Alfred Nobel stands as perhaps the most famous, became his greatest burden example of a scientist whose invention, the Swedish chemist and inventor, didn't set out to become the merchant of death. His goal was simple and seemingly beneficial: create a safer, more stable explosive that could be used for construction, mining, and industrial development without the constant threat of accidental detonation that plagued existing explosives. Working in the shadow of family tragedy, Nobel was haunted by the 1864 explosion that killed his younger brother, Emil, during experiments with nitroglycerin. The incident drove him to develop something better, something that could harness the incredible power of nitroglycerin without its deadly unpredictability. His solution was ingenious. By combining nitroglycerin with diatomaceous earth, he created a stable explosive that could be safely transported and precisely controlled. He called it dynamite. The invention made Nobel incredibly wealthy and famous throughout Europe. Dynamite revolutionized construction, enabling the building of tunnels through mountains, the creation of harbors where none existed before, and the excavation of massive engineering projects like the Panama Canal. Nobel genuinely believed he had given humanity a tool for progress and development, a way to reshape the physical world for the betterment of civilization. But Nobel's comfortable illusions were shattered in 1888 through a twist of fate that would change everything. A French newspaper, confused about which Nobel brother had died, published Alfred's obituary while he was still very much alive. The headline read, like a condemnation from history itself, "Le marchand de la mort est mort." The merchant of death is dead. The obituary described him as a man who became rich by finding ways to kill more people faster than ever before. Reading his own obituary was like glimpsing his legacy from beyond the grave, and Nobel was horrified by what he saw. The world didn't remember him as an innovator who had made explosives safer for industrial use. Instead, he was seen as the creator of humanity's most efficient killing machine. Dynamite hadn't just revolutionized construction. It had transformed warfare, making artillery more devastating, fortifications more destructible, and battles more deadly than ever before. The psychological impact on Nobel was profound and immediate. He had spent his career believing that his invention served progress and peace. He had even theorized that creating sufficiently powerful weapons might make war impossible, reasoning that no rational leader would engage in conflict when the potential for destruction was so overwhelming. Instead, he discovered that his creation had simply escalated the arms race, making conflicts more devastating without making them less likely. Nobel's response was to completely restructure his will, leaving the vast majority of his fortune to establish prizes that would recognize achievements in physics, chemistry, medicine, literature, and most importantly, peace. The Nobel Peace Prize was his attempt to atone for unleashing dynamite upon the world, a way to encourage the very opposite of what his invention had facilitated. He wanted to be remembered not as the merchant of death, but as someone who had ultimately served the cause of human progress and international harmony. The irony runs deeper than Nobel could have imagined. While his Peace Prize has honored some of humanity's greatest advocates for non-violence and international cooperation, dynamite and its descendants continue to fuel conflicts around the world. Every modern explosive, from military ordnance to terrorist bombs, traces its lineage back to Nobel's laboratory. The very fortune that funds the Peace Prize was built on an invention that has enabled over a century of increasingly destructive warfare. But perhaps the most disturbing aspect of Nobel's story isn't what he created, but what it reveals about the nature of scientific progress itself. Nobel was a brilliant, well-intentioned man who genuinely believed his work would benefit humanity. He took reasonable precautions, conducted careful research, and approached his experiments with scientific rigor. Yet despite his best intentions and careful methodology, he created something that would enable death and destruction on an unprecedented scale. The Manhattan Project represents the ultimate expression of scientific power, turned toward destructive ends, and no figure embodies the moral complexity of this transformation more than J. Robert Oppenheimer. Known as the father of the atomic bomb, Oppenheimer was a brilliant theoretical physicist who assembled and directed the most ambitious scientific project in human history. What he created in the deserts of New Mexico would fundamentally alter the balance of global power and leave humanity living under the permanent shadow of potential annihilation. Oppenheimer's involvement in the Manhattan Project wasn't driven by bloodlust or military ambition. Like many scientists of his generation, he was motivated by the terrifying possibility that Nazi Germany might develop nuclear weapons first. The theoretical groundwork for atomic weapons had been laid by scientists across Europe, and refugees from Nazi-occupied territories brought urgent warnings about German nuclear research. For Oppenheimer and his colleagues, the choice seemed clear: develop atomic weapons for the United States, or risk letting Hitler's regime gain access to the ultimate weapon. The scientific challenge was unprecedented in its complexity and scope. Creating a nuclear weapon required advances in physics, chemistry, metallurgy, and engineering that pushed the boundaries of human knowledge. It meant coordinating the efforts of thousands of researchers across multiple secret facilities, solving problems that existed at the very edge of theoretical understanding, and doing it all under intense pressure and absolute secrecy. Oppenheimer proved to be not just a brilliant scientist, but an exceptional leader capable of managing this vast enterprise. He could discuss quantum mechanics with Nobel laureates in the morning and coordinate construction schedules with engineers in the afternoon. His deep knowledge of Sanskrit and literature gave him a philosophical perspective that helped him grapple with the moral implications of what they were creating, even as he pushed the project forward with relentless determination. The first successful test of an atomic weapon took place on July 16, 1945, at the Trinity site in the New Mexico desert. The explosion exceeded even the most optimistic predictions of the scientific team. The flash of light was visible from over 100 miles away. The heat was so intense that sand in the immediate vicinity was transformed into a new mineral that researchers named trinitite. The mushroom cloud rose over 7 miles into the atmosphere, and the shockwave was felt by observers positioned 10 miles from ground zero. Oppenheimer later described his thoughts at that moment, using a quote from the Hindu sacred text, the Bhagavad Gita: "Now I am become death, destroyer of worlds." The words captured something profound about what had just occurred. Humanity had not merely created a new weapon. They had unlocked one of the fundamental forces of the universe and turned it toward destruction. The power that fueled the stars themselves was now contained in a device that could fit in the bomb bay of an aircraft. Less than a month later, that power was unleashed on the Japanese cities of Hiroshima and Nagasaki. The results were more horrific than even the scientists had anticipated. The immediate death toll reached into the hundreds of thousands, but the true scope of the devastation became clear only gradually. Radiation sickness, cancer, and birth defects would affect survivors and their descendants for decades. Entire city centers were obliterated, leaving shadows burned into concrete where human beings had stood at the moment of detonation. For Oppenheimer, witnessing the actual use of atomic weapons was a profound shock. During the bomb's development, he had focused on the scientific and technical challenges, treating it as an abstract problem to be solved. He had assumed that if the weapons were ever used, it would be as a demonstration of power rather than against civilian populations. The reality of Hiroshima and Nagasaki forced him to confront the true implications of what he had helped create. The psychological toll on Oppenheimer was immediate and lasting. He began speaking out against the development of even more powerful hydrogen bombs, arguing that the United States already possessed sufficient nuclear capability to deter any potential aggressor. His opposition to expanded nuclear weapons programs led to accusations of disloyalty and the revocation of his security clearance during the height of the Cold War. The man who had been celebrated as a national hero for winning the race to develop atomic weapons was now viewed with suspicion by the very government he had served. Einstein's role in the development of nuclear weapons was more indirect than Oppenheimer's, but his sense of regret was equally profound. The great physicist never worked directly on the Manhattan Project, but his theoretical insights laid the groundwork for understanding nuclear fission, and his personal intervention helped convince President Roosevelt to support American nuclear weapons research. Einstein's famous equation, E equals mc squared, had revealed the enormous energy contained within matter itself. When nuclear fission was discovered in the late 1930s, Einstein immediately understood the implications. If the nucleus of an atom could be split, the energy released would be proportional to the tiny amount of matter converted, multiplied by the speed of light squared. Since the speed of light is an enormous number, even a small amount of matter could release devastating amounts of energy. The realization that nuclear weapons were theoretically possible filled Einstein with dread, particularly given the political situation in Europe. He was a German Jew who had fled Nazi Germany and understood better than most the implications of such weapons falling into Hitler's hands. When fellow physicist Leo Szilard approached him about the possibility of German nuclear weapons research, Einstein agreed to write a letter to President Roosevelt, urging American development of atomic weapons. Einstein's letter to Roosevelt was brief but compelling. He explained the theoretical possibility of nuclear weapons, warned about potential German research in this area, and urged the United States to begin its own nuclear was too late. The weapons program before it letter helped convince Roosevelt to approve the funding and resources that would eventually become the Manhattan Project. But Einstein's fears about German nuclear weapons proved to be largely unfounded. While German scientists had discovered nuclear fission, their weapons program never advanced beyond the theoretical stage. Germany's nuclear research was hampered by limited resources, scientific disagreements, and the chaos of wartime conditions. By the time the United States successfully tested its first atomic weapon, it was clear that Germany had never posed a serious nuclear threat. This realization filled Einstein with profound regret. In later interviews, he described writing the letter to Roosevelt as the greatest mistake of his life. He had helped unleash nuclear weapons on the world based on a threat that never actually materialized. If he had known that Germany would not develop atomic weapons, he said, he would never have supported the American nuclear program. The irony was particularly bitter for Einstein because he had spent his career as a pacifist, an advocate for international cooperation. His scientific work had always been driven by pure curiosity about the nature of the universe, not by any desire to create weapons or serve military purposes. Yet his theoretical insights had provided the foundation for the most destructive weapons ever created, and his political intervention had helped bring those weapons into existence. Marie Curie's discovery of radium opened entirely new frontiers in physics and chemistry, while simultaneously exposing her to radiation that would ultimately claim her life. Her pioneering research into radioactivity earned her 2 Nobel Prizes and established her as one of the most accomplished scientists of her era. But the very substances that brought her scientific fame also demonstrated the double-edged nature of scientific discovery. Working with her husband Pierre, Marie Curie spent years processing tons of uranium ore to isolate minute quantities of radium. The work was physically demanding and extraordinarily dangerous, though the full extent of radiation's harmful effects wouldn't be understood until decades later. The Curies worked in poorly ventilated laboratories, handling radioactive materials with their bare hands, and storing radium samples in their home where they would admire the mysterious blue-green glow in the darkness. The immediate effects of radiation exposure were subtle but unmistakable. Curie began experiencing chronic fatigue, unexplained bruising, and wounds that refused to heal properly. Her fingers became permanently scarred from handling radioactive materials, and she developed a persistent cough that grew progressively worse over the years. Despite these warning signs, she continued her research with characteristic determination, convinced that the benefits of understanding radioactivity outweighed the personal risks. What made Curie's situation particularly tragic was her growing awareness of radiation's dangerous properties, even as she continued exposing herself to them. She witnessed colleagues and assistants developing mysterious illnesses that seemed connected to their work with radioactive materials. Blood disorders, unexplained cancers, and premature deaths became increasingly common among researchers in her field. Yet, the scientific importance of her discoveries compelled her to continue, even as the evidence mounted that her work was slowly killing her. The commercial applications of radium that emerged during Curie's lifetime revealed the horrifying potential for her discovery to cause widespread harm. Radium became a popular ingredient in consumer products, marketed as a health tonic and miracle cure. Companies produced radium-laced toothpaste, cosmetics, and beverages, claiming these products would improve vitality and cure various ailments. The most devastating example was the use of radium in luminous paint for watch dials, leading to the tragedy of the Radium Girls. Young women employed to paint watch faces with radium-based luminous paint were instructed to lick their brushes to maintain a fine point. This practice exposed them to massive doses of radiation, causing their jaws to literally disintegrate, their bones to become so brittle they would break from minor impacts, and their bodies to glow with an eerie green light. When these workers began developing horrific illnesses and dying in agony, Curie was forced to confront the reality that her scientific triumph had enabled systematic poisoning on an industrial scale. The psychological burden of this realization was compounded by Curie's own deteriorating health. As her condition worsened, she understood that her life's work had not only harmed others, but was actively killing her as well. The radium that had brought her international acclaim and scientific recognition was destroying her body from the inside, causing the aplastic anemia that would eventually claim her life. Her laboratory notebooks remain radioactive to this day, stored in lead-lined boxes that will be necessary for thousands of years to come. Nikola Tesla's experiments with wireless power transmission pushed the boundaries of electrical science so far beyond conventional understanding that he may have accidentally created technologies capable of devastating entire regions. Working from his laboratory in Colorado Springs, Tesla conducted experiments with electrical forces that generated artificial lightning bolts over 100 feet long and created electromagnetic disturbances that could be detected hundreds of miles away. Tesla's goal was revolutionary but seemingly benign. He wanted to create a worldwide system of wireless power transmission that would provide free electricity to anyone, anywhere on Earth. His vision was of a world where poverty would be eliminated through abundant energy, where communication would be instantaneous across any distance, and where humanity would be united through shared access to unlimited power. But the methods he employed to achieve this vision involved manipulating forces that could potentially destabilize the electrical systems of entire continents. The scale of Tesla's Colorado experiments defied all conventional understanding of electrical engineering. His massive coils generated millions of volts of electricity, creating electromagnetic fields so powerful they could light incandescent bulbs without wires at distances of over 20 miles. The artificial lightning produced by his equipment was visible from locations far beyond the horizon, and the electromagnetic pulses were so intense they overloaded and destroyed power generation equipment throughout the Colorado Springs region. Local residents reported bizarre phenomena during Tesla's experiments. Horses in nearby stables received electrical shocks through their metal shoes and bolted in terror. Butterflies flying near the laboratory became disoriented and spun in circles, apparently affected by the intense electromagnetic fields. People walking near the facility experienced static electrical charges so powerful their hair would stand on end, and metallic objects throughout the area would spontaneously generate sparks and electrical discharges. But the most disturbing aspect of Tesla's work was his apparent success in creating what he called standing waves in the Earth's electrical field. By precisely timing his electrical pulses, he claimed to have created resonance effects that could amplify his signals using the planet itself as a conductor. If Tesla's calculations were correct, this meant he had discovered a method for transmitting virtually unlimited amounts of electrical energy to any point on Earth's surface. The implications of this technology were staggering and terrifying. Tesla's system could theoretically provide unlimited power to any location, but it could also be used to overload and destroy electrical systems anywhere in the world. A sufficiently powerful transmission could burn out power grids, disable communications networks, and create electromagnetic pulses capable of destroying electronic devices across entire continents. Tesla had essentially created the first weapon of mass destruction based on electromagnetic energy. The experiments came to an abrupt end when Tesla's equipment caused a massive power failure that left Colorado Springs without electricity for days. The local power company, already strained by providing free electricity for Tesla's experiments, refused to continue supporting research that threatened the stability of their entire electrical grid. Tesla was forced to abandon his Colorado laboratory and return to New York, leaving behind equipment that was too dangerous to operate and too advanced for anyone else to understand. Tesla's later writings suggest he became increasingly aware of the destructive potential of his wireless power system. He spoke of developing defensive applications for his technology, describing how electromagnetic pulses could be used to disable enemy aircraft or naval vessels. But he also expressed concerns about what would happen if such technology fell into the wrong hands, recognizing that his discovery could potentially be weaponized in ways that would make conventional warfare obsolete and far more devastating. The Wright brothers' achievement of powered flight in 1903 was celebrated as one of humanity's greatest technological triumphs, opening new frontiers for transportation, communication, and exploration. But within just a few years, Orville and Wilbur Wright watched in horror as their invention was transformed into an instrument of warfare that would fundamentally change the nature of human conflict. The Wright brothers had envisioned aircraft primarily as tools for peaceful purposes. They imagined passengers traveling swiftly between distant cities, mail and cargo being delivered to previously inaccessible locations, and explorers reaching remote regions that had never been mapped. Their early demonstrations focused on the practical applications of flight for transportation and communication, emphasizing the potential for aviation to bring the world closer together through improved connectivity. Military interest in aviation developed almost immediately after the Wright brothers' successful flights, but initially focused on reconnaissance and observation rather than combat applications. Early military aviation was seen as an extension of existing intelligence-gathering methods, with aircraft serving as elevated observation platforms that could provide commanders with better information about enemy positions and movements. The Wright brothers initially supported these applications, believing that better intelligence would lead to shorter, less costly conflicts. But the rapid militarization of aviation technology soon revealed capabilities that far exceeded anything the Wright brothers had anticipated. Aircraft evolved from simple observation platforms to active weapon systems capable of dropping explosives, engaging in aerial combat, and conducting strategic bombing campaigns against civilian targets. The same principles of lift, thrust, and control that enabled peaceful flight also enabled the creation of fighter aircraft, bombers, and other weapons systems that would transform warfare into a three-dimensional battlefield. World War I demonstrated the devastating potential of military aviation with shocking clarity. Aircraft that had been designed for reconnaissance were quickly adapted to carry bombs, machine guns, and other weapons. Aerial combat between fighter aircraft became a deadly ballet performed thousands of feet above the ground, with pilots engaging in life or death struggles that combined the technical precision of aviation with the brutal reality of mechanized warfare. The psychological impact on the Wright brothers was profound and lasting. They had spent years perfecting the technical challenges of flight, overcoming problems of lift, control, and propulsion through careful experimentation and gradual refinement. They had risked their lives testing prototype aircraft and invested their entire fortune in developing aviation technology. But within a decade of their first successful flight, They watched their invention being used to rain death from the skies on an unprecedented scale. Strategic bombing campaigns represented the ultimate perversion of the Wright brothers' peaceful vision for aviation. Aircraft designed to carry passengers and cargo were instead loaded with explosives and sent to destroy cities, factories, and civilian populations. The ability to attack targets far behind enemy lines meant that entire populations became potential victims of warfare, not just military personnel. The distinction between combatants and non-combatants, already blurred by industrial warfare, was further eroded by the advent of aerial bombardment. Fritz Haber represents perhaps the most complex and tragic example of scientific genius turned toward destructive ends. His development of synthetic nitrogen fertilizer through the Haber-Bosch process has been credited with supporting nearly half of the current global population by dramatically increasing agricultural productivity. Yet, the same chemical knowledge that enabled him to feed millions also provided the foundation for chemical weapons that would terrorize the battlefields of World War I and ultimately contribute to some of humanity's darkest chapters. Haber's journey from agricultural savior to architect of chemical warfare began with the most noble of intentions. Germany in the early 20th century faced a looming crisis that threatened to destabilize the entire nation. The country's rapidly growing population was outpacing its ability to produce food, and traditional farming methods simply couldn't generate enough crops to feed everyone. Without a breakthrough in agricultural technology, mass starvation seemed inevitable within just a few decades. The root of the problem lay in nitrogen, an essential element for plant growth that was becoming increasingly scarce. Natural sources of nitrogen compounds were limited and expensive, forcing farmers to rely on imported fertilizers that many couldn't afford. Haber recognized that if he could develop a method for creating nitrogen compounds artificially, he could solve Germany's food crisis and potentially transform agriculture worldwide. Working under intense pressure and with limited resources, Haber developed a process for combining nitrogen from the air with hydrogen to create ammonia, which could then be converted into highly effective fertilizers. The technical challenges were enormous, requiring precise control of temperature and pressure under conditions that pushed the limits of existing industrial equipment. But Haber's process worked, and when scaled up to industrial production, it revolutionized farming across the globe. The humanitarian impact of Haber's discovery cannot be overstated. His synthetic fertilizer process enabled agricultural yields that were previously impossible, turning marginal farmland into productive fields and allowing existing farms to support much larger populations. Historians estimate that without the Haber-Bosch process, the Earth could support perhaps half its current population. Haber had literally given humanity the ability to feed itself on an unprecedented scale. But the same chemical knowledge that enabled Haber to create life-sustaining fertilizers also revealed pathways to create compounds designed to destroy life. When World War I erupted, German military leaders approached Haber about applying his expertise in chemistry to develop weapons that could break the deadly stalemate of trench warfare. The conflict had devolved into a horrific war of attrition where thousands of soldiers died for gains measured in yards, and both sides desperately sought new methods to achieve decisive victories. Haber's entry into chemical weapons development was motivated by patriotism and a genuine belief that his contributions could shorten the war and ultimately save lives. He reasoned that weapons capable of forcing quick surrenders would be more humane than the prolonged slaughter of conventional warfare. His scientific mind approached chemical weapons as a technical problem to be solved, focusing on the chemistry and delivery mechanisms rather than dwelling on the human consequences. The result of Haber's wartime research was the systematic deployment of poison gas on European battlefields. Chlorine gas, phosgene, and eventually mustard gas transformed warfare into something even more nightmarish than the brutal trench fighting that had preceded it. Soldiers faced the terror of invisible death that could seep through protective equipment, causing agonizing chemical burns, permanent blindness, and slow suffocation as their lungs dissolved from the inside. The first large-scale use of Haber's chemical weapons occurred at the Second Battle of Ypres in 1915, where German forces released clouds of chlorine gas across Allied trenches. The results exceeded even Haber's expectations in terms of tactical effectiveness, but the human cost was horrifying. Soldiers caught in the gas clouds died in agony, their bodies racked with convulsions as the chemicals their respiratory destroy systems. Those who survived often suffered permanent damage to their lungs, eyes, and nervous systems. Haber's personal involvement went far beyond laboratory and chemical weapons deployment research. He personally supervised gas attacks on the battlefield, studying the effects of different compounds and refining delivery methods based on observed results. His wife, Clara Immerwahr, herself a brilliant chemist, became increasingly horrified by her husband's work and pleaded with him to abandon chemical weapons research. Their marriage deteriorated as Haber became more deeply involved in developing increasingly deadly chemical agents. The tragedy reached its peak when Clara Immerwahr took her own life in 1915, using Haber's service pistol to shoot herself in their garden. Many historians believe her suicide was directly motivated by her husband's role in chemical weapons development and her inability to convince him to stop. Haber discovered her body and was reportedly devastated, but rather than abandoning his weapons research, he threw himself even more deeply into his work, perhaps as a way of avoiding the psychological implications of what he had created. The long-term consequences of Haber's chemical weapons research extended far beyond World War I. The industrial processes he developed for producing chemical agents were adapted and refined by subsequent researchers, leading to increasingly sophisticated and deadly compounds. His work provided the foundation for nerve agents, blister agents, and other chemical weapons that would be used in conflicts throughout the 20th century. Most horrifically, the same industrial chemistry knowledge that Haber had used to create fertilizers and chemical weapons was eventually perverted into tools of genocide. The gas chambers of the Holocaust employed Zyklon B, a pesticide that was developed using principles directly derived from Haber's chemical research. The irony was unspeakably cruel. A Jewish scientist's discovery was used to implement the systematic murder of millions of his own people. Haber's final years were marked by increasing isolation and regret, as the full implications of his scientific legacy became clear. Despite his contributions to German military technology, the rise of Nazi Germany forced him to flee his homeland, due to his Jewish heritage. He died in exile in 1934, a broken man who had witnessed his greatest discoveries being used for purposes that violated everything he had originally hoped to achieve. The case of Arthur Galston demonstrates how even the most benign scientific research can be twisted toward destructive purposes through applications that were never intended or anticipated by the original researcher. Galston's work began with a simple desire to help farmers grow better crops in challenging conditions, but it ultimately contributed to one of the most environmentally devastating military campaigns in modern history. Working as a graduate student in the 1940s, Galston was investigating plant growth regulators, chemical compounds that could influence how plants developed and matured. His particular focus was on soybeans, which were becoming increasingly important as both a food source and an industrial crop. The challenge he sought to address was extending the growing season for soybeans, allowing farmers in northern climates to cultivate varieties that had previously been limited to warmer regions. Galston's research led him to discover that certain synthetic compounds could dramatically accelerate plant flowering and fruit production. By applying these growth regulators at specific stages of development, farmers could potentially harvest crops weeks earlier than normal, opening up vast new areas for cultivation and allowing multiple growing seasons in regions where only one had been possible before. The agricultural implications were enormous, promising increased food production and greater farming flexibility. The compound that would later become notorious as Agent Orange emerged from Galston's investigation into plant hormones and their synthetic analogues. He found that specific concentrations of these chemicals could not only accelerate plant growth, but also cause rapid defoliation under certain conditions. Initially, this side effect seemed like a minor curiosity with limited practical applications. But military researchers who learned of Galston's work recognized the potential strategic value of compounds that could rapidly remove vegetation. Dense jungle canopies had always provided natural concealment for military forces, and the ability to quickly clear large areas of forest cover could provide significant tactical advantages. What had been discovered as an agricultural tool was reimagined as a weapon for denying enemy forces their natural camouflage. The transformation of Galston's plant growth regulators into military defoliants involved scaling up production and modifying delivery systems. But the basic chemistry remained unchanged. The same compounds that could help soybeans mature faster could also strip the leaves from entire forests when applied in sufficient concentrations. Military planners envisioned using these chemicals to expose enemy supply routes, eliminate hiding places, and force opposing forces into open terrain where conventional weapons would be more effective. During the Vietnam War, Agent Orange and related compounds were deployed on an unprecedented scale across millions of acres of Southeast Asian forests. The environmental devastation was immediate and visible. Vast areas of dense jungle were transformed into barren wastelands within days of chemical application. But the long-term consequences proved to be far more severe and lasting than anyone had anticipated. The ecological damage extended far beyond simple defoliation. The chemical compounds persisted in the environment for decades, contaminating soil and water supplies across huge regions. Wildlife populations collapsed as their habitat was destroyed and food sources were eliminated. Agricultural areas that were accidentally exposed to the chemicals became unsuitable for farming, contributing to food shortages and economic disruption that continued long after the war ended. Human exposure to Agent Orange produced health effects that wouldn't become fully apparent until years after the war concluded. Both Vietnamese civilians and American military personnel who had been exposed to the chemicals began developing unusual patterns of cancer, birth defects, and neurological disorders. The full scope of these health impacts is still being studied decades later, with new connections between Agent Orange exposure and various medical conditions continuing to emerge. For Galston, watching his agricultural research being used as an instrument of environmental warfare was profoundly disturbing. He had devoted his career to understanding how plants grow and develop, motivated by a desire to help farmers feed growing populations more effectively. Seeing that same knowledge being used to destroy forests and poison landscapes violated everything he had hoped to accomplish through his scientific work. The psychological burden was compounded by the scale and persistence of the damage. Unlike conventional weapons that cause immediate but localized destruction, the chemical defoliants continued causing harm for generations after their initial use. Children born decades after the war ended still showed birth defects linked to Agent Orange exposure, creating a legacy of suffering that extended far beyond the original conflict. Galston spent his later career advocating for restrictions on chemical weapons and environmental warfare, drawing on his unique perspective as someone who had contributed to the underlying science but never intended its destructive applications. He testified before Congress about the long-term dangers of chemical defoliants and worked to establish international agreements limiting the use of environmental modification as a weapon of war. The development of increasingly sophisticated surveillance and control technologies has created new categories of scientific regret among researchers whose innovations have enabled unprecedented violations of privacy and human rights. Unlike the dramatic weapons and industrial chemicals that characterized earlier scientific controversies, these modern technologies often appear benign or even beneficial in their original applications, making their transformation into tools of oppression particularly insidious. Facial recognition technology represents a perfect example of this pattern. The underlying research began with legitimate goals, helping law enforcement identify suspects from security footage, enabling more secure access control systems, and assisting people with visual impairments in recognizing faces and objects. The technical challenges were fascinating from a computer science perspective, involving complex algorithms for pattern recognition, machine learning systems that could improve their accuracy over time, and databases capable of processing millions of images in real time. Early applications seemed entirely positive. Missing children could be located more quickly when their faces were spotted by surveillance systems. Airport security became more effective at identifying individuals on terrorist watch lists. Banks could prevent fraud by verifying that customers matched their identification documents. The technology promised to make society safer and more secure, while reducing the burden on human operators who had previously been required to manually review vast amounts of surveillance footage. But the same capabilities that enabled these beneficial applications also created unprecedented opportunities for social control and political oppression. Governments quickly recognized that facial recognition technology could be used to track the movements of entire populations, identifying individuals at protests, monitoring their daily activities, and creating detailed profiles of their social connections and political affiliations. What had been designed as a tool for security became an instrument of surveillance that would have been unimaginable just decades earlier. The deployment of facial recognition systems in authoritarian countries has demonstrated the technology's potential for enabling systematic human rights violations. Citizens can be tracked everywhere they go, their associations monitored, and their behavior analyzed for signs of political dissent or social nonconformity. The technology has been used to identify and persecute ethnic minorities, suppress religious freedom, and maintain social control through constant surveillance that makes privacy virtually impossible. These 10 brilliant minds remind us that scientific discovery is never truly neutral. Every breakthrough, every moment of revelation, every leap forward in human understanding carries within it the seeds of both creation and destruction. The same knowledge that can heal can also harm. The same principles that build can also destroy. And the same curiosity that drives us toward enlightenment can also lead us into darkness we never intended to explore. The question that haunts every true scientist isn't whether they can make a discovery, but whether they should.